students, welcome to our another online session for the course Computer Organization, and today we are going to discuss the processor and its internal architecture and how we're going to design the processor. We're going to discuss the basic component of the processor in detail, and we will review what we've studied till now because we have designed the data path for the R format instructions, the I format instructions, the loads and stores and branches, and how to deal with jumps, and we're going to review those contents or revise those contents formally so that we can continue with our discussion, and we will discuss our pipeline processor, and then we're going to compare the performance of both the systems in terms of speed up. So to start with our discussion, we are basically on chapter number 4 of the book, and this is Computer Organization and Design, the Hardware Software Interface, the fourth edition. The slides are basically the book slides, which we will gonna follow for rest of our discussions. So to start with our discussion, we know that the processor is basically the key component in computer system, and that is the device that is responsible to process all the data and instructions and in order to execute any task or to perform any task. And along with other components, processor is also the important component, and that is the primary system component. By the primary system component, we mean that, or the devices, we mean that our computer system will not going to run without those components that are known to be the primary system components. So processor is one of the key component. So let us first see what are the performance factors. The CPU, that is the central processing unit performance factors, that basically determines the performance of the processor. So we have discussed while we were discussing the assembly that the instruction count is important. That tells us the instruction count, basically that is known to be the IC. In our previous discussion, while we are computing the performance parameters for a single processor, or we are comparing the system with other processors, we are basically, when we are computing the execution time, if you remember that execution time is equal to, execution time was equal to or we can also call it a CPU time, that was equal to instruction count multiplied by CPI, that is cycles per instruction, which we are following, and whole thing multiplied by clock cycle time, or divided by the clock frequency of the system. So instruction count is important, and the second thing, we determine the instruction count is determined from the instruction set architecture and compiler. Basically, we have discussed that what sort of instructions we are going to use in order to process our task, and what sort of compiler we will use in order to process those instructions. The second important thing which you can see from this formula is that is the CPI. That are the cycles per instruction, what number of cycles from the processor we are on average consuming in order to process those instructions, and cycle time is important. So these are the key factors that basically determines our performance of the system. Instruction count is basically determined on instruction set architecture and compiler, and the CPI and cycle time are determined upon the CPU hardware. So the CPI and cycle time, basically that depends upon what sort of hardware component we are using, and what are the factors, for example, on what clock rate the processor is being operating, and what are the resources which we are using with that specified processor. So CPI and cycle time depends upon that. So in our discussion, we've discussed the two MIPS implementation we will discuss, and the first version is a simplified version, that is a single cycle processor, which we have discussed before our second sessional examination, that is a single cycle processor. And if you remember that why we call it a single cycle, because it's going to process all the instructions in one clock cycle, that's why we call it a single cycle. And in that system, in that particular case, the CPI was 1, if you remember that. If all the instructions are executing in one clock cycle, then CPI of that system is known to be 1. Then we're gonna, after discussing or revising the single cycle processor, we'll switch to the pipeline version of the single cycle processor. That is basically the more realistic version. We will discuss that. So, but for that, if you have got the knowledge of the single cycle processor, then it will help us a lot. So in our discussion, we will be basically seeing how we're going to deal with memory references. And while we are saying that, we have to see the memory references. Either we are reading the memory or we are writing the memory. So load word basically reads your memory and moves the data towards the processor, and store words basically writes the memory, and data is moved from processor towards the memory element. Then we're going to see arithmetic and logical operations. For example, how we're going to implement add, subtract, and shift left, shift logical left, you can say that. And we've discussed that while we were discussing how to implement the R format instructions, I format instructions, J format instructions in detail. And last but not least, we're going to discuss about the control transfer instructions. For example, that instructions which can transfer the control from one point to another point. Otherwise, our execution is basically sequential execution. For example, we have discussed that we've got specific instruction 1, for example, then 2, then 3, and so on and so forth. And normally our execution is in sequential order, but some instructions can change the order of execution for a program. For example, the branch equal instruction, that is a conditional instruction, and that may or may not change the sequential flow of execution depending upon the condition is been satisfied or not. And second is the jump instruction, just like the go to instruction in C++, or you've studied about x86 architecture. We've got some unconditional jump instructions. So these are the instructions that can change the sequential flow of execution of our program. So we're going to discuss that in detail as well. Now, how the instruction has been executed, if you remember that we've got a detailed instruction cycle, and we've discussed that instruction cycles contains the process or the steps or methodology in which our instruction is being processed by the processor. First of all, we have to fetch our instruction, then we have to decode our instruction, then we have to execute our instructions, then we have to write our results either in a memory or some dedicated resources. So uh, our data path or our processor should have the capability to process all those dedicated steps in order to process the instruction cycle. While coming to the instruction execution, first of all, we're going to fetch the instruction. That is the important step. And from where we're going to fetch our instruction, definitely we have seen that we have got a dedicated memory source that is responsible to hold our instruction or machine code basically for the instruction. So that is known to be the instruction memory. And how we're going to access those instructions, we've got a program counter. Basically, that is a dedicated hardware component that provides the addresses for those instructions. Afterwards, we're gonna read the operands basically, and operands we're gonna see where those operands are basically kept. So we've got a register file that contains the operands, either the source or destination or target operand, depending upon the operation which we are performing. So we have to read those registers, and for reading, we have to access the register file. Then depending upon the instruction class, as we've seen that instruction can be divided into R format, I format, or we can say that depending upon the nature of the operation. Our data path or the process that we're going to follow in a single cycle processor can vary, and the functional units that basically are the hardware components our data path comprises of. So their utilization can differ depending upon the instruction. Depending upon the instruction class, we're gonna use the hardware component that basically execute our instruction. That is basically the arithmetic logic unit. ALU is the key component basically that basically execute our instruction. So that component is responsible to generate the arithmetic result if that is required. The second thing is we can have the memory address computation, for example, the physical address computation for loads and stores, in which we have to add the base with offset address. That is also been done with the ALU. And also, last but not the least, the branch target address that is also being computed with the ALU. Then afterwards, if we've got any dedicated instructions that require the loads and stores in order to read or write the memory, then we're going to access the memory that contains our data. And in our case, we've got the data memory. So we've got a data memory, just like the instruction memory, that basically deals with all the data references that are required for the program. And afterwards, we're gonna address our program counter either with the target address in case of branch instructions, or in case of jump instructions we've got a different sort of address, or in a normal execution flow we're going to add the program counter with a value of 4 in order to generate that particular address. Well, coming to the next slide, this is the basic structure or the basic components that are being used in a single cycle processor. Why we call it a single cycle? We've discussed earlier that all the instructions are processed in one clock cycle. That's why we call it a single cycle. And those sort of processor has the CPI, that are the cycles per instruction equals to 1. So if you see the basic structure here, these are the basic modules, and definitely with the passage of time, these modules, some of the new modular components are going to be added in this processor. So if you see that this is a section that is used for the instruction fetch, we can say that fetching is done from here, and we have discussed that the instruction memory is a memory that contains the machine code for the program, and program counter is the basic component that provides the address of the location from which we have to fetch the instruction. So the next address, how we're going to generate the next address, that is dependent upon the type of instruction. But for the time being, let us assume that for the sake of our simple discussion, we have to add 4 in it. So we can see that this is the adder module that adds the value 4. If I just highlight that in a current value of the program counter in order to generate the next value. We're going to discuss this at the functionality of this adder later on, but this is just to show that if we have to add something into any component, we have to use adders. So the graphic representation of the ALU is also similar to the adder. Basically ALU is responsible to perform the arithmetic and logical operations. So we represent the ALU in the same fashion as we represent the adders in the same fashion. After we've got the instruction fetched, we got the machine code. The next step is to read the operands. Here we got the machine code, and for MIPS32 we've got a 32-bit machine code of any particular instruction. Next thing is to read the operand. So this is the compartment. This is the compartment basically that contains all our registers. The registers are physically implemented here. Normally in architectures, we can either classify the register file into simple register file, or that can be a physical register file. That is dependent upon how the registers are particularly being implemented. So for the sake of our simplicity, we simply assume that that is a compartment that basically holds all our information or the registers that are being implemented here in this section. Once we've got the operands here from the register file, the next thing is to execute, and as we've said that is also dependent upon the nature of instruction. Either we have to get the operands from the register file, or we have to extract the operands from the machine code. Later on we will see how we're going to extract the operands from the machine code itself, and the operation is specified here, is being performed by the ALU. And the next thing is if we've got any sort of data references, then we've got a data memory here, and then how we're going to write the results in either the registers or memory. That is also dependent upon the instruction itself and the structure of our single cycle processor. So these are just the basic components which we're going to modify later on depending upon the requirements of the instruction itself. Right now, if you see the previous diagram which you've discussed, that you can see that this particular interconnection here, that basically creates problem in our system. How that going to create the problem? Just think of that, where the data has been moved. Basically, if you see that in this particular junction or node, either the data has been routed from this adder, or this adder is responsible to provide the data. Now which data will move here? If you've got the two options here, so we've got a sort of mechanism, selection mechanism, that basically selects when we have to give this PC plus 4 to the program counter, or we have to add some other data into the program counter. So here these are the problematic nodes here. Basically we have to resolve that, and we have to use multiplexers. Basically that are the devices that basically selects among your choices, and depending upon the selection criteria which you've provided. So we have to use multiplexers in order to select our data in order to avoid this issue. Now, how we're going to control that? Basically, we've seen the basic component of the single cycle processor, and we've seen that we've got a dedicated controller of the device, so that basically controls the operation of the processor. So normally we've got a control unit. This is the control unit that basically controls all the operations depending upon the operation code that you have provided, which you get from the instruction memory. And how the data has been processed by this single cycle processor, that is determined by the control unit. Control unit is basically a finite state machine, and that basically reacts depending upon the opcode which the machine has received, and gonna process or coordinate the operations, which module should act in which manner. So that is the responsibility of the control unit. So that basically acts as the brain of the system. Well, that was all for the today's session. In the next session, we'll continue our discussion starting from the control unit, and we're going to add our instructions step by step in order to implement, in order to enhance the functionality of our single cycle processor.